Good morning, people. And let us start with the day's lecture. Those who have joined in, let us wait for a couple of moments for more people to join. Those who have joined can post their attendance. Those who have joined can post their attendance, please, in the chat box. Yeah, please post your attendance in the chat box. Okay, Veda, Rutuja, Mukta, Sujal. 1, 2, 3, 4, 5. Okay, where are the others? I don't know. Should I start or should I wait for some more time? I'm not very sure. But let me start. Well, yesterday, or rather till yesterday, we were doing the interior of the Earth, and we actually learned how the interior is, what is it made up of, and what else? Okay, you'll see that the density of it and the physical state of it. And how do we come to know all this? We came to know about all this through seismic activities, and as far as these seismic activities are concerned, we went into the details of these also, earthquakes particularly, and we tried to understand what makes these seismic activities that dangerous. Having said that, uh, we also saw the various ways in which these waves travel, the energy travels, I would rather say, rather than saying the waves travel. And we spoke about the body waves, and we spoke about the ground waves. And then we came to how we are going to measure them. And in the process of measuring them, we classified a quantitative way of bringing up a scale chart and a qualitative way of bringing up the scale chart as such. Okay, quantitative is the energy released, and that is measured on a Richter scale, and the Marcelli scale actually uses the observations as far as destruction is concerned, and that is how you actually blend this. And then we moved into the effects of the earthquake in various ways, and finally its position in the cycle of geomorphology as such. Now, interestingly enough, we need to go further and link this to. Okay, normally, you'll see that when you see about any topic, as a matter of fact, it could be uh, any subject as such, geography included in that. We have our syllabus divided into various topics and chapters and so on and so forth. So we have touched upon the first topic as such, and going by the logic as to why do I have such a set these topics lined in my syllabus as such, would mean that I would have to check the logic between the various topics, isn't it? So why did I check or go into checking the interior of the Earth? We know that the crust is something that is being modified and modeled on something that is coming from the within. That's endogenetic processes, and earthquakes and volcanoes and associated activities are nothing but a part of that. So before I start studying the crust of this particular planet, it becomes necessary that I understand what is the source of development of this particular planet as such, and as a consequence, I did my basic studies as far as the interior of the Earth is concerned. Not that I've seen the interior of the Earth, but then I take help of the seismic studies that have come up with reference to the interior of the earth, and that is how all that is put to use. After having studied the interior of the earth, I come back to the crust, and I need to study the crust of the earth as well. And for studying the crust, I need to look into a few things. Let me share this with you. And sorry, I will be back in just a moment. Okay, there we are. Now, as far as studying the surface of the earth is concerned, I will just, for a moment of time, uh, mark the attendance of these guys, Shubham and Prithviraj. Okay, so we move to trying to understand how we are going to link the interior of the earth to the surface. So you'll see that whenever we start with studying uh, geomorphology as a matter of subject, okay, I start with the source of all this material. It could be the coastal areas and these caves and stacks and so on and so forth. It could be the dunes, or it could be volcanoes, etc. Where does the source of all this lie? All of this lies in the interior of the earth. So I need to study the composition of the structure. Then I need to come to the earth's surface and study its composition and structure. Now fortunately, we compared the composition of the interior and the surface, and we'll see that on the surface you have more oxygen as compared to iron in the interior of the earth, and then you have silicon, and then you have iron, and so on and so forth. This leads to formation of the crust, and on the crust we are going to have these landform features, which are actually an output of erosion and deposition. Now we're going to link these, but before we link this to our subject matter, we need to understand a few things as such. The geological time scale, which we have discussed in detail, and having understood the geological time scale, we need to go into a bit of geomorphological theory also. Now, I know that these slides are a bit up and down, but we'll have to jump from one slide to other, in the sense that uh, yeah, in geomorphology, we tend to understand river activities and wind activities and wave activities and glacier activities as such. Now, why is the study of geomorphology that important? You'll see that once I study geomorphology, I come to know the geomorphic processes or geomorphological processes as such. And these processes have two sources. These processes have sources from the interior of the earth, and these have sources from the exterior. And what you see as geomorphic features is basically a balancing that tries to, there is no perfect balance between them, but you'll see that because both of them are dynamic, there always to be happens to be a friction between the endogenic forces or endogenic processes and exogenic forces or exogenic processes as such. Now, the slide that I showed you, all these are exogenic. Now, how are these exogenic? Why are these exogenic? We need to go into the logic of that as well. And when I'm speaking about endogenic, I need to understand that endogenic processes is nothing but say the interior of the earth, the energy that is in the interior of the earth, and the dimensions that this energy in the interior of the earth brings us in the form of earthquakes and in the form of volcanoes. And we saw that you have millions of earthquakes every day of a very small, so small adjustments keep on taking place every now and then over the surface of this particular planet, and that brings about the dynamism of this particular planet as such. Okay, why is it that the Earth is not similar to other planets like the Mercury and the Venus and the larger planets like Saturn and Jupiter? Okay, it's because that it has its energy and from the interior, and then this is equally opposed by the energy from the exterior. Now, this energy that we call as exogenic, okay, which I gave you examples of, these are outputs of exogenic forces. This is basically because of that layer of earth that the earth has around it, which is called as the atmosphere. So all that Okay, the atmosphere directly is responsible for what generate as exogenetic process. Okay, we will gradually move into that. Then you'll see that we tend to detect with knowing geomorphology, we tend to detect natural and environmental hazards more efficiently, like earthquakes and flooding and landslides and tsunamis and volcanoes and etc. So it becomes very important. Now, there is a very interesting anomaly, I would say, in understanding endogenic and exogenic forces as such. So you'll see that while human beings, when they study these, okay, you'll see a river is something that constructs a river plane and so on and so forth. So we look at a river as a constructive force, but geomorphology looks at a river and other sources as a destructive forces. Exactly opposite to this happens when we are looking, human beings are looking at endogenetic processes like a volcano and earthquake. A volcano and an earthquake obviously is extremely powerful both earthquake and volcanoes are looked upon as constructive processes and not destructive. And human beings look at them as destructive processes and not constructive. And geomorphology looks at a river as a destructive process, while human beings look at as a river as a constructive process. So it's the perception that needs to develop in that particular way. Then it also helps us to identify various landforms and features and landscapes. You'll see that the moment you somewhere you say that, okay, this is a mountainous terrain, or this is a plateau, or this is a river plain, and within the river plain at a lower scale, you have these various features like the meanders that you speak about, the oxbow lakes that we speak about, and the berms that are there as far as the sides of a river plain, etc., is concerned. So we get to learn and identify these various landforms and features and landscape through learning geomorphology as such. Okay. And in fact, you'll see that we can identify these landforms, many of these landforms, through satellite images also. It helps in uh, research, of course, and of course, something that is related to the second point, that's we handle hazards efficiently in the form of earthquakes, floods, landslides, tsunamis, volcanoes, basically because geomorphology helps you in vulnerability studies as well. So that's something that makes up or builds up the importance of geomorphology. Now, we speak about the definition of geomorphology is basically the earth and the study of the earth. Okay, scientific study of landforms. Okay, now just scientific study of landforms would not help, basically because we have already done that as far as school levels is concerned. But that is more of informative studies that I tend to by heart the features that are there in the upper course of a river, the middle course of the river, and the lower course. I know that in the upper course I'm going to have a waterfall. As a matter of fact, I would have a pothole. As a matter of fact, in the middle course, I've just said we have a meander, and in the lower course, I'm going to have a delta. But how do they happen? Why do they happen? The processes that shape them also need to be studied, and in fact are studied as far as geomorphology is concerned. It is a composite science. Okay, it gives us an idea into the processes that cause and alter the landforms, and that's why understanding the endogenic processes and understanding the exogenic processes is very important. And you'll see that geomorphology as a subject is studied in geography, that's physical geography, geology, geodesy, engineering geology, archaeology, and geotectonic engineering also. Okay, you see that these are the various landforms which occur out of, let us say, exogenic processes. You'll see that a wide river here that narrows down into a V channel, a canyon sort of a thing. This is a desert here. Okay, and you'll see that while this is a depositional feature of wind erosion, number six here is a erosional feature of wind erosion. And then you have these coastal processes, and you have these waves which lash the lands, and of course they come up with cliffs, and they come up with caves, and so on and so forth. And number four here is glaciers, the glaciers. So it's very interesting to note here that when we speak about these landform features, water plays a very important role. Of the six diagrams that you have in front of you, or I would say the six photographs that you have in front of you, you'll see that number one has water in that, number two has water in that, number five has water in that, and number four obviously has solid water in that as well. It's only number three and six which will not have water in that, but in fact it's only when water takes a back seat that wind takes a front seat, and wind starts operating in the form of an erosive agent. Okay, so this is what we need to understand when we are doing into geography, just geomorphology in physical geography, and not just trying to say list the features and by heart the features and present them. Okay, what is the logic behind them? What is the commonality, okay, amongst these land features? Who shapes the land features? How are these land features shaped, and so on and so forth? So this is something that needs to be done. Now there is one interesting thing that we need to know, that as far as the study of geomorphology is concerned, not all has been well for a long period of time. Not all has been well in the sense that the perception of geomorphologists in looking into geomorphology has been varied in the sense. Now, what does that mean? Okay, you'll see that normally we have this issue about what are we actually going to study when we what is the source of the study as far as this the whole process of geomorphology is concerned. There are two say schools of thought. Okay, one school of thought follows what is called as uniformitarianism, while the other follows what is called as catastrophism. Now catastrophism is an older concept in geomorphology, and possibly it came to being and discussed because of the fact that man, when he started roaming around this particular planet, all he observed immediately was floods. What he observed was landslides. What he observed was earthquakes. What he observed was volcanic activity. So all of these were destructive, and that is why he thought that the base of geomorphology should somewhere be in catastrophism. Okay, and and thus an idea came. See, floods come suddenly, earthquakes come suddenly, volcanoes don't give you a warning as such. So all geologic change occurs very suddenly, and that is why this theme came to be known as catastrophism. Okay, and this also believed that the Earth is only a few thousand years old. In fact, we missed that out when we were doing, say, the studies on geological time scale. It's very interesting to see how the age of the Earth went on increasing as such. It's a very fantastic story about the process in which the technology helped in measuring the age of the Earth as such. Because you'll see that till 400 years ago, we believed that the Earth was just a few thousand years old, and its own say processes of development in science, particularly chemistry, to start with convective currents and the convective cycles that we spoke about as far as the interior of the Earth is concerned. When they were studied, they said, okay, probably it's not a few thousand years old; it's a few million years old as such. But then we came across radioactivity, and you'll see that as far as radioactivity is concerned, it proved that it's not a few million years old. It's going to be very, very more many million years of old as such. And gradually, we went on to try and understand the age of the Earth. And eventually, as of today, we don't know. Tomorrow, there could be a new technology which explains the Earth is older. But as of now, we know that the Earth is around 4.6 billion years of age, and larger forms of life have been there for the last 600 million years on this particular planet. So these were the studies around catastrophism as such. But then there in around the 18th century, okay, 1788 to be more precise, James Hutton came with his theory of the Earth, and he says that the processes that we speak about in geomorphology have been common through time. Okay, and time, he says, it is immemorable time. In the sense, he was referring to millions and millions of Earth. He says that a river may have been there a few million years ago. A river is going to be there today, and its processes are going to be similar to what it was in the previous age as such. And of course, in future times to come, a few thousands and millions of years to be down the line, a river is obviously going to be the same. So the processes that operate on the surface, similar things go with volcanoes, similar things go with earthquakes as such. There have been earthquakes in the past, there have been earthquakes in the present, and there will be earthquakes in the future, and other activities as such. And that is what happens is that the processes in geomorphology are actually uniform. They have been there. And of course, he also says that it takes a long time. Gradual geologic, these are gradual geologic processes, and these are not sudden catastrophic movements as such. And this is what his disciple, his follower Charles Lyell, in 1830s, he continued, and he brought up a very famous academic work called Under Principles of Geology as such. And in fact, it is this erosion, this deposition, the process of mountain buildings through folding, mountain buildings to volcanic eruption, mountain buildings to endogenic processes. All of this do prove the fact that Earth is not a few thousand years of age, but it is a few billion years old as such. So that is something that anybody who is initially working into physical geography, geomorphology, needs to understand these two cycles, or rather these two school of thought, as far as geomorphology is concerned as such. And you'll see that this is normally called as a geomorphic cycle as such, that you have molten rock from which you are going to have magma rising, and this comes up in the form of igneous rocks. When it comes up, it is going to be called as an extrusive rock. When it lies within, solidifies within the crust, it's called as intrusive rock as such. Okay, and this is going to be eroded and transported and deposited, leading to formation of sedimentary rocks. These sedimentary rocks are once again set to melting, or they are uplifted and brought up to the surface. So this is what continuously keeps on happening. Of course, the arrangements, now this is a volcano, and you'll see that energy balances within them is going to be earthquakes, so endogenic forces. And then of course, buildup of these mountains is going to be a small local happening as such. And then exterior processes like water falling and the river flowing and the river eroding and transporting material to form deposited sediment is a very interesting, makes this a very interesting cycle as such. If you remember, I've just said that radioactive processes within the core provide a lot of energy that is required for many activities that tend to happen on the surface as such. That brings us to the importance of geomorphology and the exogenic geomorphic processes, and where all do we apply our geomorphic knowledge as such. We've already said it has a lot of social reference, in the sense study of the processes that make up land features and landscapes, and of course studying environmental, or rather detecting and handling environmental hazards, what is called as vulnerability studies as such. So this is another way of say it has a social relevance of geomorphology, and the interactions between geomorphology and human activity. You'll see that in this photograph here. Okay, this is the human activity, and behind that you have the natural activity in geomorphology. If I remove this, obviously this is going to come down, so I try to control the geomorphic processes as such. Okay, not that I am able to control it every time, but yes, I tend to, I am able to do it many a times as such. And further, you will see that I can go for topographic and thematic mapping, a survey of lands, natural hazards, landslides, avalanches, earthquakes, and land subsidence as such. Engineering designs, you can see a very interesting engineering design here. Construction of a dam, okay, constructed in a very artistic way as such. Okay, so all this, okay, is helped with if we are obviously having a sound knowledge of geomorphology. It's not that I just it's not an artistic impression, I would rather say, that I find and I like something, and I want to have a dam somewhere. I have to go for the groundwork, uh, the type of rocks and the type of surface and the amount of water that could be accumulated, and what is the environmental destruction that may be caused out of this. All of this needs to be understood in the whole process. And in fact, your knowledge of geomorphology is going to help in all these supportive actions as such. Okay, then, uh, As we speak about the surface of the Earth, I'm not very sure whether, sorry, yeah, as we speak about the surface of this planet as such, okay, we need to understand how the origin of the Earth came into process, and there are various theories as such. You have the gaseous theory, and we have the solar theory, and the Big Bang theory, and so on and so forth. Of course, geography does not take you all that. Geography starts when, okay, Earth, study of the Earth. So it's after the process of the formation of the Earth, surface of this planet, that we start with geography. What happens before that goes into geology. Not that we completely discard it. We need to know the links into the origin. But we don't go into much of details as far as the origin of the Earth is concerned. Once the Earth is formed, we know that for a few hundreds of initial million years, the Earth was in a semi-solid state as such, and we had a lot of volcanic eruptions on the surface, of course, leading to a lot of earthquakes also. And thus gradually the surface cooled down, and this cooling led to the scum of this whole process, very lighter and less dense material coming up, what we later started calling land surfaces as such. And uh, we started studying about these land surfaces, and when we studied these land surfaces, we found out some anomalies. Now, what were these anomalies? These anomalies were pointing out at a fact that possibly the continents are on the move. Okay, and why should we say that? Okay, there were many theories of climate change even in those times and today. They said that there are evidences which show that there are some contradictory evidences, in the sense that let us say that you could find a marine fish fossil. Rather, they found a marine fish fossil in the Himalayan ranges. Now, the Himalayas are such a distance from the Bay of Bengal or the Arabian Sea or even the Pacific Ocean or the Indian Ocean. How is it possible that marine fossils could be found high up in the Himalayas? One thing. Then you saw that in deserts you tried to study, and you found fossils of evergreen trees in the desert. Similarly, you found desert remnants in evergreen forests, and so on and so forth. So these were very confusing uh, evidences as such. Now, so they tried to conclude that there are two reasons for this. That one could be an external reason, that there have been regular climatic changes, and what was a rainy area in the geological past becomes a dry area today, and so on and so forth. It's one thing. And then there could also be an endogenetic force which keeps on operating, and because of this operation, the continents are on the move, is what is said as such. Okay, and scientists kept on studying various studying all these processes through various expeditions and explorations, and they brought in various say evidences and tried to confirm them through research papers, etc. And this went on for tens and tens of decades and decades together. Okay, and all this effort came out in small studies here and there. When we meet tomorrow, obviously, I'm going to speak about this and more. But I'll go back into the history, but then I would start at a point which is there as a part of your syllabus, and that is the continental drift theory. This continental drift theory is something that a German scientist, Alfred Wegener, came up with in 1910 or 11, I suppose. It was translated in English, and it's when it came to be translated in English that it gained more popularity. Now, it's very interesting to note how Wegner came up with this particular theory. Not that he was actually working on it, he had his students around him, and they had cut the shapes of various continents. And one of the students pointed out that, sir, if we try to play jigsaw puzzle with the shapes of these continents, do you think that these continents would fit into each other? And that gave Wegener that idea of trying to see whether the continents are fitting into each other. And eventually he comes up with this whole process, which he calls as that All the continents were together at some point of time around 200 million years ago, and that single continent was called as Pangaea. And then he divides them further and so on and so forth. Now, further studies have shown that it is not the only time that the continents have merged together to form a single solid mass of land surface. In fact, what keeps this in operation, the interior, the energy in the interior of the Earth, okay, it runs into cycles. So it is believed that every 1 billion year there is a cycle of all the continents coming together, and eventually they go apart from each other. Okay, now if we leave aside the first billion years where the Earth was actually moving into a solid formation, we could say that the rest of the 3 billion years that we add up to leads to the fact that there could have been at least two more cycles of unification and separation of all the continents together. So, what Wegener is referring to, Pangea and his idea of continent and etc., is actually believed to be the third time. Okay, before that you had Rhodania 1, and before that they say that you had Rhodania 2, and in future again we believe that a few hundreds of millions of years down the line we could have all these moving together. And studying all this is a very interesting way to of looking at geography as such. Now, obviously the seed of the continents being on the move was sown by Wegener. So scientists started speaking about various theories around them. Now, while many scientists speak about continents moving horizontally, there were a few theories. There rather is a theory which speaks about the land masses moving vertically up and down also. That is called as the theory of isostasy also. That's not a part of your syllabus, but then sorry, that is what isostasy is all about. And that the movement this way, and the movement this way is continental movement. Now you'll see that there has been a lot of, though you have only I think the continental drift as a theory, there have been a lot of development as far as understanding the movement of continents over the period of time is concerned, and this was linked with various other developments, technological developments. Now, it's so very funny and amusing to understand that not every time were scientists looking for evidences into continental movement. They were doing something else, and while that was being done, they came across these things. Say, for example, they were trying to lay down a telegraphic cable between Europe and the America and North America, so that communication could be faster. And while they were making a study of how this could be done, they came across a ridge in the center of the Atlantic Ocean. In fact, that is called as the Mid-Atlantic Ridge as such. And they found that in further studies, as far as the rocks of these ridges are concerned and the processes along the ridge, they found that many of the points along this particular ridge was volcanically active. So they thought that okay, is the uh, Earth actually divided into lithospheric plates rather than continental plates? What Wegener was referring to. Wegener was referring to only land and water, but now you'll see that gradually they said that what is there beneath the oceans also is a part of land. It's only that it is covered with water, and that is why you don't call it as a land. And so they said that possibly it's not only land, but land extends above the water, but land extends beneath the water also. And it is these land surfaces which are broken into what are called as plates. The lithosphere that we studied as far as interior of the earth, okay, that is the thickness of the upper 100 kilometers, is what is referred to as plate tectonics as such. And while Wegener speaks about this around 1912, confirmation of plate tectonics etc comes around 1956 onwards as such. So a lot of research study continuously has been going around this as a matter of fact. So understanding all this becomes very, very interesting. And though all of these theories are not there, I've given you the names of various theories, and then in between the plate tectonics on one side and the the real start of it, I would rather say, the continental drift theory of Wegener. There are a few theories before that also, which I will just touch upon when we meet yesterday. And then there are a few theories between them, which eventually lead to the plate tectonics. Now, there is one major difference between the theory of plate tectonics and the theories before plate tectonics as such. While the theories before plate tectonics, you would say you have the continental drift theory, which is named after Wegener. Then you have the Holmes convectional current theory, and so on and so forth. You'll see that you have the Suez theory, and so on and so forth. You'll see that no single scientist actually claims the say the propriety of plate tectonics, basically because even today, okay, 60, 70 years down the line after plate tectonics was first introduced, thousands, I would say thousands of scientists all around the world keep on working around confirmation of more evidences as far as the plate theory of plate tectonics is concerned. And that is why you'll see that while other theories, okay, though we will refer to Wegener's theory, there are a lot of flaws in the Wegener's theory. Eventually, other theories also. Okay, and that is why new theories came up and old theories took a back seat. This doesn't happen with plate tectonics. You'll see that plate tectonics is a theory which tends to be upgraded regularly. Okay, and it is encompassing because it is a cumulative work. It encompasses and brings about a lot of development regularly that happens through time in every corner of this particular planet. So that's a very fantastic thing. It's a cumulative work of geoscientists in different parts of the world. Unfortunately, because that's a part of an intensive study of geomorphology, it's not a part of your syllabus. You're going to do the plate tectonic theory for our purpose as it is noted in your syllabus, and that's going to be all. But those who would be more interested, obviously, I would suggest them to go and read about plate tectonics and the latest in plate tectonics more so. So. Being a holiday today, I would not like to stretch all the way to 10:20 for the day. I will stop here for the day, and I'll just check the names of those who came in later so that I have them as a record with me. Okay, Adesh Jadhav, Ashish Jadhav. That's interesting names. Shiva, this is what Manasi, Kadambari, Vijay Kadam. Okay, so I've marked most of the attendees that came and left. Okay, obviously I see that now this girl Mauli Kade has also joined in. Uh, However, I don't see that the whole process, the attendees have at any point of time gone beyond 10. Anyway, I give the benefit of doubt to the students, and at least these students who have made an attempt to join the regular class as such. Having said that, today we have gone back to trying to understand the basics of geomorphology once again, and why do we study geomorphology? What is the say the importance of the study of geomorphology, and how is it connected to the day-to-day life, your and mine day-to-day life, right from a dam to construction of a road to avoiding a landslide, all this, and then we went back again into time into the two schools of thought as far as approaches to geomorphology is concerned, and that is how we came to the theories on of what are called as formation of crustal theories as such. And these theories are divided into various sub theories, okay, of which we are supposed to be doing one is what I said as far as the whole process of continental drift theory is concerned. But that obviously is going to be for some other time. I am thinking of an activity that could be done for tomorrow morning 7 o'clock lecture. Let me think around it, and if it runs fine, I would announce the schedule of what we are supposed to be doing at 7 o'clock in the morning tomorrow. That's all for the today. And if you don't have any questions, if you have questions by now, you should have posted it in the comment box. But if you don't have any questions, let us call it a day, and I would be ending my broadcast here. Thank you very much. Have a good day.